So let's recap. These are the proof techniques that we've seen so far in this class. Can someone tell me what a direct proof is? Sure.
Just like start with the statement you want to prove and then show that it's true.
Right. We're given some collection of facts that we're allowed to assume, and from there, we somehow deduce that the statement we want to prove is true. Okay? It's as straightforward as it can be. There's not a whole lot of symbolic stuff that we can write for discrete proofs. Okay? What's a proof by contradiction? Can someone remind me? Yes?
We assume the opposite of the statement.
Yeah.
Then we do a series of valid statements. And if the series of valid statements yields a false statement, that means the assumption has to be false.
Perfect. Yeah. So if we want to prove some statement S, and the statement could be anything, something like the square root of 2 is irrational, or it could also be something like something of the form of an implication. What we do with the proof by contradiction is we assume the opposite of it. Okay, so we assume that the statement we want to prove is false. Okay, and from there we'll make a series of steps, just like we did with the square root of 2 proof, and we'll arrive at some form of contradiction, right? So show some contradiction, implying not S is false, i.e., what's going on here? i.e. S is true. Good. What about a proof by contraposition? Someone else maybe from the back? What's a proof by contraposition? Yes?
If we have like P implies Q,
Yeah.
say that not Q implies not P.
Good. So we do a proof by contraposition if the statement we want to prove is of the form P implies Q. Okay? And what we do is we show this by, by showing not Q implies not P. Okay? And you had a lot of practice with this in the homework. Okay, and then counterexamples. Can you use a counterexample to prove something? No, right? Instead, you use a counterexample to show that something is not true. Okay? So to prove that something is true, you need to be more rigorous and do it generally, but a counterexample can be used to show that something is not true. Okay? And so today what we're going to do is talk about proof by induction. Okay, it's the last sort of proof technique that we need to cover formally, but it has the most nuances. There's the most steps, right? The other ones are relatively straightforward, but there's sort of this pattern that you'll see in a lot of most proof by induction problems, and it's sort of unintuitive at the very beginning. Okay, but let's go through it. Okay, so what's a scenario in which we might want to use proof by induction? Okay, so suppose you're sitting in a massive room, right? Maybe not this one because this room's not that big, and there's like thousands and thousands of rows, and you want to figure out what row number you're in, right? You could stand up, go to the front, be like, okay, this is the first row, this is the second row, this is the third row, and count all the way until you're. You could do that, right? But what you could also do is set up this sort of game of telephone, right? Where the first person in the room knows by default that they're in the first row. Is that clear? Right? So that's our base case. And where does this term base case, where's the other place you've heard of this before? Recursion, right? So you should be thinking of recursion right now. Because induction and recursion, there are many parallels between them, okay? So the person at the very front of the room, they know they're in the first row. So that's assumed by default. And then, how can we transmit information from person in row n to person in row n plus 1? Well, you just tell the person behind you your row number plus 1. Is that clear? So suppose you're in the first row, you know you're in row 1. Otherwise, if you're in some random row, not random, but arbitrary row, the row of the person behind you is your row number plus 1. Is that clear? So that's like our base case and our recursion step, right? The row of the person behind me is my row number plus 1. Is that clear? Any questions with that? Okay? So let's formally define what induction is then, okay? So we use mathematical induction to prove properties about all natural numbers, okay? Not necessarily all. Sometimes we'll start at 0, which if you remember is not a natural number, but instead it's a whole number, but that definition Like in terms of induction, we usually include 0 as being a natural number, but it usually depends on the statement itself. So sometimes it'll say, prove for all natural numbers greater than 3 that this property is true. And then your base case would be 3. Okay? But in most cases, it'll be 0. So induction has these 3 steps, right? So we have the base case where we establish that the statement holds true for the smallest possible case, right? And that, in our example, was the person in the first row in the room knows their row number by default, right? There's no calculation that needs to be done, okay? Then we have our induction hypothesis, okay? And this is where we sort of take this leap of faith and just flat out assume the statement is true for some arbitrary number k, okay? So you can't plug in some specific value for k. You can't say, okay, it holds for k is equal to 5. That's not what we mean by arbitrary. We leave k as a variable and just assume the statement holds true for n being equal to k. Okay, and this will make a lot more sense when we look at a concrete example on the next slide. Okay, so our second step is this induction hypothesis. We're just assuming that it's true for n is equal to k. And then our induction step is where most of the work gets done, okay? So most of the work is here. And this is, in like when you talk about this in 628 and recursion, this is how you make a larger problem smaller. So this is how you use the information you have in a smaller problem, right? Just like in Fibonacci, you know 5 factorial is equal to 5 times whatever the result of 4 factorial is, right? That's similar to what we're doing in the induction step. We're assuming that the statement holds true when n is equal to k. And now we're going to do some manipulation to show that it holds true for n is equal to k plus 1. Okay? So our 3 steps, we just established some base case that we have to check manually. Our induction hypothesis, where we assume it's true for some arbitrary number k. And then our induction step, where we use the information that it's true for n is equal to k and show that it's true for n is equal to k plus 1. Yes?
So the recursive leap of faith, that would be
The hypothesis.
okay.
Yeah. So that's a term that the 628 GSIs like to use, this recursive leap of faith. You just hope that it works in the recursive case, and all of the work that you need to do is figure out some way to combine cases together, how to make your problem smaller. That's what we're doing with the induction hypothesis and the induction step. Our leap of faith is assuming that it's true for some arbitrary k, and then all of our work will be showing that if it's true for n is equal to k, it has to be true for n is equal to k plus 1. Okay, and we'll look more at the logic of why this actually works in just a minute. But first, I want to get into an example. Okay? How many people already knew that this identity was true? That the sum of the first n natural numbers is n plus 1 over 2. Okay, how many people have never seen this before? Okay, about 50-50. Okay, so we want to prove that this is true. So what's our first step? And we're doing this with induction. So what's our first step? Our base case, right? And in this case, what is our base case? Yes?
The sum of 1 is 1.
Right. So in our base case, n is equal to 1, right? Because the smallest value of I in our sum, there should be an I here. Okay, because what was there before, it didn't make sense, because it was the sigma logo, not the logo, but the symbol, that means we're summing some values, but it didn't have a value to sum there. So we needed this I there. Okay? Right here, the smallest possible value of I we can work with is 1. So the smallest n we can work with is 1. Okay? So our base case is when n is equal to 1. Okay? Is this identity true when n is equal to 1? Well, let's look at the left side and right side separately. Okay? What is the sum from I going from 1 to 1 of I? What does that look like? The sum going from I is equal to 1 of just I. It's just 1, right? Just like the sum of going from I is equal to 1 to n of I is 1 plus 2 plus 3 all the way until n, because our upper bound was n. Here our upper bound is just 1, so our value is just 1, and the sum of the number 1 is just 1. Okay, what's our right-hand side? It's this expression, 1 times 1 plus 1 over 2. What's that? 1, 2 over 2. is equal to 1. Does the base case hold? Yep. So therefore, base case holds. Okay? And you'll notice a pattern in how I write these induction solutions, both in the textbook and here. And I want you to get used to writing induction problems, the solutions to induction problems in the same way. I want you to explicitly write base case, then solve the base case. Then induction hypothesis, and write specifically what you're assuming. And then induction step, and write specifically the math you're doing to show that it holds true for k plus 1, assuming k. Okay? So base case. Now I'm going to have induction hypothesis. And what am I going to do in my induction hypothesis? Right? And in the induction hypothesis, I assume that it holds true for n is equal to k. Okay? So I'm going to do exactly that. Assume that 1 plus 2 plus all the way until k is equal to, maybe I'll write it down here, is equal to k times k plus 1 over 2. Any questions with that? So I'm not assigning a value to k, I'm just saying for some arbitrary k that we know nothing about, other than that it's a natural number, we're going to assume this is true. Sound good? Okay, so now here's where we actually have to do stuff. Induction step. Okay? So we can start off with this fact, because that's all we know, right? And we want to somehow show that when you sum it all the way till k plus 1, it's equal to what? Okay, we know that when you sum it from 1 to k, it's k times k plus 1 over 2. So maybe I should write this in a different order. So we can start with this. We want to show that what? The sum 1 plus 2 plus 3 all the way until k plus 1 is equal to what? Yes?
K plus 1 times k plus 2 divided by 2.
Is that clear? So that's exactly what we would get if we plugged in k plus 1 into this formula for n. Is that clear? So that's what we want to show. We're assuming that it's true for the value of k, and we're somehow going to arrive at the fact that it's true for k plus 1. Is that clear? So we're assuming this statement right here. Where can we go from there?
Add k plus 1.
Right, we can add k plus 1 to both sides. So now we have 1 plus 2 plus all the way until k, plus k plus 1 is equal to k times k plus 1 over 2 plus k plus 1. Now what can we do? Any ideas? Yes?
Prove about the two statements,
Right.
right?
I mean algebraically, how can we proceed? We could bring them to a common denominator, right? So what I could do is this part doesn't change. K times k plus 1 over 2. And how do I bring k plus 1 to the same denominator as over 2? I just multiply top and bottom by 2. So I have 2k plus 1 over 2. And then I have a common factor of k plus 1 here, right? So I can factor that out. And I have k plus 1 times, oh, look at that, k plus 2 over 2. Okay? And we've shown exactly what we wanted to show. We wanted to show that the sum from I equals 1 to k plus 1 is equal to exactly what I've highlighted here. And we did that. We started by assuming that it's true for some arbitrary value of k, and then manipulated that to show that it's true for our value k plus 1. So therefore, induction holds. That's a statement you'll see a lot. Yes?
How do you go from the second line to the third line?
So this line to this line?
No, above it. Like from the box to
Yeah.
the one below it.
I added k plus 1 to both sides.
Okay.
I guess I can write that here. Add k plus 1 to both sides. Good. Any questions with what we did here? Cool. And so, of course, we're going to go over several more examples. But I wanted to look at this in terms of propositional logic, okay? So what's our base case? Well, we're showing, so assume that P at n, or P at 0, P at 1, represents our proposition holding true for whatever values in the parentheses, right? So, I don't know. Assuming that it's the sum 1 plus 2 plus all the way until k is equal to k times k plus 1 over 2, that's assuming that pk is true. Our base case was showing that p1 is true. And what we did in the inductive step is showing that pk implies pk plus 1. Is that clear? So if we just let p at whatever represent our proposition evaluated at a specific natural number, then this is exactly what we did. Base case, we show that P of 1 holds true. Induction hypothesis, assume that PK holds true. And in our induction step, we showed that if PK is true, then PK plus 1 is true. Sound good? Any questions with that? Okay, so that's exactly what it says here. In our base case, we show that okay, so here it says P0, so it could be P of 1. It depends on the question, okay? So it depends on proof. Okay? Our induction hypothesis, assume that P of k holds true. And then in our induction step, we show that P of k implies P of k plus 1. Perfect. That's exactly it. And so it's a little difficult to decipher if you're not familiar with the notation, but hopefully by now it somewhat makes sense, okay? And just to be a little more precise, replace this with for all n in the naturals, or the whole numbers for now, okay? So what this is saying is, if the base case is true, and for any k you give me, P of k implies P of k plus 1, then this proposition is true for all natural numbers. Okay? So we're showing that it's true for the very smallest case, we're showing that it's true for P0 or P1, and that given any k, k plus 1 is true. Well, using that, if we have both of those pieces, and we know that P of 0 is true, well then we can show that P of 0 implies P of 1. But then again, we can show that P of 1 implies P of 2. And then we can show that P of 2 implies P of 3, so on and so forth, because we have this piece. Right? So all we need, in addition to having that P of k implies P of k plus 1, is we need some base case to be true. And then once we have 0, we can plug in 0 and get that P of 1 has to be true. Once we have 1, we can plug it in again and show that P of 2 has to be true, and so on and so forth. Is that clear? Yes?
So let's say we prove something.
Sure.
And we take our base case to be, let's say, P of 3.
Okay.
And then we prove it, and then we do the P of k implies P of k plus 1.
Okay.
Then can we say anything about P of 2 or P of 1?
So there you'd implicitly be assuming that k is greater than or equal to 3. Is that clear? So usually when we do our base case, it's the smallest possible value for which the proposition will hold true. So if it happens to be the case that the smallest possible value in which we care about, that the proposition holds true, is 3, then when you do your induction hypothesis, you're assuming that k is greater than or equal to 3, because 3 was the smallest case that we cared about. In this case, the smallest case we cared about was 1, right? But it won't always be 1. Any questions with this? So we have our base case. We know that P of k being true tells us that P of k plus 1 is true. So this, we can chain them together. We have 0 means 1 is true, 1 means 2 is true, 2 means 3 is true, so on and so forth. Any questions with that? Yes?
Why can't you choose between 0 and 1?
It depends on the question. So you can't necessarily choose. It's just the smallest natural number for which this sentence is true.
Does
Okay.
P1 holds, but implies that P1, P0 holds?
No, so it doesn't work in the backwards direction. It just, your base case is whatever the smallest possible value is that your proposition holds true. So in this case, notice our proposition of n is just the sum from 1 to n. But 0 wouldn't make sense here. Like, what would the sum from 1 to 0 be? Right? So in this case, we say our base case is 1, because it's the smallest possible case in which this is true. So your base case is the smallest one, okay? Oftentimes it's 0 or 1, but maybe in the question it might say something else. Like, for example, in your homework, there's a question where you prove that the sum of the interior angles of a polygon is 180 times n minus 2. Okay? Like triangle, the sum of the interior angles is 180, quadrilateral it's 360, so on and so forth. But there, you assume n is greater than or equal to 3, right? Because a polygon has to have at least 3 sides. Is that clear? Yes.
The choice of your base case limits your proof.
So you don't. It's not that you get to choose, but it's that based off of the proof, you have to make it like you have to identify what the base case is. Okay. So like, given the question that you're required to prove, the base case will be clear. It's not that you arbitrarily choose it. It's just whatever the smallest possible value that your proposition holds true for. In this case, it's 1. In the case in the homework, it'll be 3. Most of the time, it will be 0 or 1. Usually 1. Is that clear? Okay. How can we derive this? So when we did the proof by induction over here, we were already given the statement, and we were just asked to show its validity. Okay? But we didn't come up with it from scratch. Okay, so other proof techniques, like if you prove something directly, you can often use some method to come up with it from scratch. Okay? But induction, you're only ever given the statement in its entirety, and you're asked to show if it's valid. So my question is, can we think of a way of just starting with this, i.e. pretend we didn't know this. Pretend we didn't know the right-hand side. How could we come up with this expression? And so I can think of like 4 or 5 different ways that you could do this. And I actually want to add a section to the textbook where it just goes over every different way you can prove this. Okay? But what we're going to do is like the classic way of proving this. Okay? So there's some story, some random mathematician, like Gauss. Okay, so you know it. His teacher was like, yo, go add up 1 to 100 real quick. And he says 50-50, and the teacher's like, how'd you do that? And he did what we're about to do. Okay? So let's start off by writing our sum as 1 plus 2 plus blah, 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 until n. Okay? By the way, who knows exactly what I'm about to do? A couple people. Okay, so it'll still be a surprise for some people. Okay? And our job is to just find an expression for find an expression for s in terms of n. Okay? So what's a possible step I could do from here? And like, don't say use the formula for the sum of an arithmetic series. Like, you can also derive that by doing exactly what we're about to do. Well, what's another step? Okay, so you could rearrange it. So you have to be a little clever with this. So you know what? Let me space these out. Okay. And I'll admit, if you haven't seen this before, this is going to seem like I'm just pulling this out of nowhere, but it's okay. We'll do it. Okay? So watch what I'm about to do. Instead of writing them 1 plus 2 plus 3 all the way until plus n, let me reverse them. So let me write it as n plus n minus 1 plus n minus 2 plus 2 plus 1. Okay? So you have 2 expressions for s. Both are identical. Let's add down. On the left-hand side, what do I have? 2s. The right-hand side, notice each of these pairs has the same sum. What is that sum? N plus 1, right? So I have n plus 1 plus n plus 1 plus all the way until plus n plus 1. So how many n plus 1s are there? N, right? Because I have all the way from 1 to n. But that gives it that s is equal to n times n plus 1 over 2. Right? So we didn't do this with induction. We just started with, this is more of a direct proof, right? We started with just the expression 1 plus 2 plus 3 plus all the way until n, and somehow came up with this expression at the end. Okay? So this is a direct proof of the same thing. And in the homework, there's another type of direct proof that you'll use to prove the exact same thing. And it's called a telescoping sum. Has anyone heard that term before? Okay, a couple people. So you can use that to prove sums of the form like 1 plus 2 plus 3 plus all the way until n. But you'll also use it to prove 1 squared plus 2 squared, all the way until n squared, or 1 cubed plus 2 cubed, all the way until n cubed. So you'll have fun with that in the homework. And those aren't necessarily induction questions per se, but they're related, and I think it's important that you get exposed to those kinds of stuff. So any questions with this derivation? Cool. Let's look at another example of an induction problem. Okay? So the Fibonacci sequence is defined by two first terms, so f of 1 and f of 2, both being 1, and f of n is equal to the sum of the previous two terms. So f of n minus 1 plus f of n of minus 2. Okay? And so we want to prove that the sum of the first n Fibonacci numbers is equal to the n plus 2th Fibonacci number minus 1. Is everyone clear what we're trying to prove? Okay? So I'll give you a couple minutes, work amongst yourselves, and try and construct a proof of this. And then we'll take it up. Okay, let's come back together and take it up. So can someone tell me what the base case is? Yes?
The sum of your first Fibonacci number, which is just 1,
Yeah.
is equal to the sum of the third. Well, the third Fibonacci number, which is 2 minus 1, which is
Good. So our base case is when n is equal to 1. What's our left side? Well, it's just the first Fibonacci number, which is 1. What's our right side? Well, it's the third Fibonacci number minus 1. What's the third Fibonacci number? It's 2, and 2 minus 1 is indeed 1. So therefore, the base case holds. Good. What's our induction hypothesis? Well, so we're going to assume that the sum from I going from 1 to k of f of I is equal to the k plus 2th, k plus 2nd Fibonacci number minus 1. Any questions with that? Yes?
Do you also prove base case that n is equal to 2?
No. So I get why you're asking that, because the Fibonacci numbers are defined with two base cases, because f of 1 is 1 and f of 2 is 1. Can someone answer that question? Why do we not have to prove two base cases for this question? Because that's a good point. Some questions will have multiple base cases. And we can look at examples of those in discussion on that. So does anyone have an answer to that? Why do we not have to show two different base cases for this question?
We're just like defining some property of some given sequence. We're not like creating it from scratch.
Exactly. The thing we're proving has nothing to do with how the Fibonacci numbers are defined. We're just saying that the sum of the first n Fibonacci numbers follows this pattern. We're not saying anything about the Fibonacci numbers and how they're defined. Good question. Okay, so our induction hypothesis is assuming that the sum of the first k is equal to the k plus second one minus 1. So now what's my induction step? Induction step. Someone else, maybe. No offense. Sure.
Could you like separate out fk plus 1 to like the definition of the Fibonacci number?
Okay. That's part of what we can do, but what exactly are we trying to show right now? What is required of us? Like, what are we being asked to show? Yes. Yes, we want to show that f of 1 plus f of 2 all the way until f of k plus f of k plus 1 is equal to what? F of k plus 3 minus 1. Okay, so that's what we're required to show. That's our goal right now. Is that clear? Sounds good. So let's start with what we know. So start with the IH, which is that if we sum from 1 to 2 to k, we get f of k plus 2 minus 1. Where can we go now? Any ideas? Sure.
Replace f of 1 plus f of 2 all the way to f of k, all the way to f of k to equal f of k plus 2 minus 1 in the original induction step, the one in red.
So we can't exactly do that yet because we have to start off with assuming what we know from the induction hypothesis. We eventually want to somehow end up at this. So we can't assume what's in the red yet. We need to start off with what we know and somehow get to what we have in the red. Good question. Yes?
So we add f of k plus 1 to each side.
Good. We can add f of k plus 1 to both sides. So add f of k plus 1 to bs. So now what do we have? We have f of 1 plus f of 2 all the way until f of k plus 1 is equal to what? F of k plus 1 plus f of k plus 2 minus 1. And now is where we use the definition. What is f of k plus 1 plus f of k plus 2? F of k plus 3. By definition. And the minus 1 still sticks around. Okay? So therefore, induction holds. Because that's exactly what we wanted to show. We wanted to show that the sum of f of 1, f of 2, and all the way until f of k plus 1 is equal to f of k plus 3 minus 1. So what we did is we start off with just our induction hypothesis, right? And make changes to it that eventually lead with us showing that it's true for k plus 1. Is that clear? So this three-step formula really will not change. 1, prove that the base case is true, which is what we did when showing that f of 1 is, it holds when n is equal to 1. Step 2, we assume that it holds for some arbitrary k. So I guess we can write this. We show p of 1. Here we assume p of k. And here we show p of k implies p of k plus 1. Sound good? Yes?
It's pretty obvious, like from the sequence of numbers, that f of k plus 1 plus f of k plus 2 is equal to f of k plus 3.
Sure.
What allowed you to assume that? Like, how did you come up with that?
That's from where, that comes from the definition of Fibonacci numbers right here.
Okay, so you just, I get that, but like, you just make that assumption at that point.
It's not an assumption, it's true for sure. Because for any n, f of n is equal to f of n minus 2 plus f of n minus 1. So that's just a definition that's true. You can use that, yeah. That's not part of what we're trying to prove. So I guess, yeah, that's a given. So this is not what... That's a good point, because we happen to use the same variable n there, and so you might misinterpret the statement that I've highlighted in the blue as being part of what we want to prove. But it's not. That's part of the definition of the Fibonacci numbers themselves. What we want to prove is this statement right here. And that's what we did. Sound good? Yes?
Does something have to tie f of k plus 3 back to f of k plus 2?
No, not necessarily. Like we've completed the proof. We just, what we wanted to show is that if you plug in k plus 1 in for n here, that it holds. And that's exactly what we did. Right? So if you replace n with k plus 1, that's exactly what we showed. Because we have k plus 1 is equal to k plus 3 minus 1. And that's what we showed here. So we don't have to do anything else.
So we don't need to establish the equality between n and k?
So what we're doing with our induction hypothesis and induction step is assuming that it holds true for n is being equal to some, not random, but arbitrary k,
Oh,
and then show that if it's true for n being equal to k, then that implies that it's true for n being equal to k plus 1. Anything else? Cool. So here's an example, and this is probably the last thing we'll do today, yeah, of an induction problem that doesn't necessarily have anything algebraic as part of the proposition itself. Okay? So we're assuming that there are two n plus 1 airports where n is an integer, positive integer. Okay? So remember, we're doing induction on n. Okay? But there happen, like, for whatever n you give me, there are two n plus 1 airports. Okay? The distances between any two airports are all unique. Okay, so just imagine some random grid such that the distances between all the points are different. Okay? For each airport, there's exactly one plane leaving it and going to the closest airport. Prove with induction that there is an airport with no planes coming towards it. Okay? So all the distances are unique. A plane of every airport finds the airport that's closest to it and sends an airplane to it. Show that there's always an airport with no incoming planes. Is everyone clear on the problem itself? Okay, so this one's interesting. I'll give you a couple minutes to talk about it, and then we'll take it up. Okay, let's come back together. So what's the base case? Can someone tell me? Sure. So base case, n is equal to 1. But if n is 1, how many airports are there? 3. So 3 airports. Okay, and so can you reason about why the base case is true? Anyone? Sure.
You can think of like a scalene triangle.
Okay.
And each point on the edge is an airport.
Yeah.
So you'll see from the shortest length, those airplanes will go across each other.
Perfect.
The one on the farther end is going to just go to the closest. Like.
Exactly. Was everyone able to hear that explanation? So consider a scalene triangle. And so that's exactly a triangle where all 3 sides have different lengths. Okay, let me just draw some random scalene triangle. Okay, maybe that's not scalene. Okay, sure, that's scalene. Okay? All 3 distances are unique. And so what happens is that the 2 points that are closest to one another will send airplanes to one another. Is that clear? So what's the shortest side here? Well, it's this one. So this airport will send a plane that way. This airport will send a plane that way. Therefore, this airport has no incoming planes. Is that clear? So the base case is true. Just think of it as a triangle with all side lengths being unique. By default, like if you have 3 integer side lengths, one of them has to be the smallest. And the 2 points that are on either side of the smallest line segment, they send airplanes to one another. So that third point has no incoming plane. Sound good? Okay. Now what's my induction hypothesis? Any ideas? Well, we're going to assume this holds true for n is equal to k. So holds true for k plus 1, or 2k plus 1 airports. Okay? And now what's my induction step? We want to show it's true for n is equal to k plus 1, i.e. 2k plus 3 airports. Okay, so our induction hypothesis is that we're assuming it's true for some arbitrary k. So this schematic holds true for 2k plus 1 airports. With 2k plus 1 airports, there's one airport with no incoming planes. Okay? Now, how can we show that it's true for some set of 2k plus 3 airports? So this question is slightly different than any of the ones we've done before. So before, we started only with the information in our induction hypothesis and added or rearranged terms until we got to our inductive step, right? We started with, I don't know, the sum of the first k Fibonacci numbers and then added the k plus 1th Fibonacci number to both sides. Okay, but we're going to do something different here. Any ideas? Yes?
I don't know, could we maybe like put the two new airports right by the like lone airport and then go back to the triangle thing?
Okay, so you're saying, so we have to involve our induction hypothesis somehow, right?
Yeah, well, we assume that the statement holds for like some
2k plus 1 airports.
collection of airports.
Okay.
We just take the lone one and then put two little ones beside it. Like,
Okay, and
so,
what would that
so
do?
that they both like point to it or something. I don't know.
You're on the right track.
Yeah.
Yes.
So when we have 2k plus 1 airports, there's going to be one airport that has no incoming airplanes.
Yeah.
So if we add just one more airport, then it will be possible to have like every airport have a receiving airplane.
Okay. We don't know necessarily that that's true.
No, if we add one airport,
Okay.
it's always going to be possible.
We don't know that though.
Yeah, but then if we add a second airport,
Okay.
then
I see what you're saying. You're saying you add one airport, and then now they all have someone to send an airplane to. Then you add another one, and that's the one that's alone. That's kind of what you're saying. Okay, interesting idea, but not quite. Yes.
Couldn't you just take 2k plus 1, because that was our induction hypothesis,
Yeah.
and then say k equals k plus 1 and then plug that in?
No. So we want to show that it works with k plus 1. We can't assume that yet. We can only assume that it's true for k. Okay, so what we're going to do is start with 2k plus 3 airports. Okay, 2k plus 3, not 2k plus 1. But we're not going to assume that it's true. Okay, think about that for a second. Why does that work? Right? So we're going to start with the collection of 2k plus 3 airports. We don't know that the statement holds for 2k plus 3 yet, because that's what we're trying to show. But given our collection of 2k plus 3 airports, what do we know? Yes?
If you somehow prove that since it's odd, there aren't even numbers, there isn't an even number for every rental that they're receiving.
That's sort of what he was talking about when you add one airport and then add another. Okay? Yes?
So, like, if you assume 2k plus 3 is false, then 2k plus 1 can't be true.
Not quite. So the statement is a true statement. You'll never be asked to do induction on a statement that's false. Yes?
Could we possibly say, like, in our induction hypothesis, for the 2k plus 1 airports, there's one airport that's left over?
Yeah.
And so, if we use that, we can say for the 2k plus 3, for the 3 airports left over, it's kind of like the base case.
Exactly. If we start with 2k plus 3 airports, we know that all the distances are unique. So we can just remove the 2 airports that are closest to one another. And what happens when you remove 2 airports from 2k plus 3? You're left with 2k plus 1, which you know is true by the induction hypothesis. Is that clear? So we remove the 2 airports that are closest together. You're left with only 2k plus 1, which is true by the induction hypothesis. So I know an initial concern will be, but doesn't it seem like you're assuming the thing you're trying to prove? But we're not assuming that the statement holds true for 2k plus 3 airports, right? We're just assuming that we have 2k plus 3 airports. We don't necessarily know that there will be one airport left over. We don't know that yet. We're just starting with a collection of 2k plus 3 airports, saying that by definition, 2 airports have to be closest to one another. And if we remove those 2, the remaining airports, of those, there will be one left over, right? Is that clear? So we're not assuming what we're trying to prove yet. Because if you assume what you're trying to prove, that's not a valid proof. We're just saying that we happen to have 2k plus 3 airports, and when we remove 2 of them, of the remaining, there will be one left over. Is that clear? Okay? So, therefore, induction holds. So, let me erase this. Just say, note we don't assume okay? So again, it's important to realize this distinction. We're not assuming that it holds true for 2k plus 3 airports. We're just assuming that we have 2k plus 3 airports. Okay? Okay, so that distinction is very important. Okay? Any questions with this? Okay, is there anything else I wanted to do? No. So that's it for today. The video will be posted later tonight. If you have your 61B exam tomorrow, like how many people have 61B tomorrow? Okay, good luck to everyone. And we'll see you on Monday.
Good luck. God bless Paul Norman.